Hello everyone, my name is Mikhail Makarov. Today I will talk about expanded decomposition in dynamic streams. This is joint work with Mikhail Kapralov and Arnold Filtser. To understand what expanded decomposition is, first I need to introduce some definitions. We say that G is a graph on n vertices and m edges, and for this graph G, a cut S is just some subset of its vertices. There's a couple of useful definition measures for a cut S. First is its volume S, and the volume of S is just equal to the sum of degrees of vertices in S. Another useful definition is size of a cut, which I denote by WGS complement of S, and this is the number of edges connecting S and complement of S. Finally, the most important definition is the sparsity of a cut. The sparsity is equal to its size divided by the volume of the smaller cut of the size. For example, on this picture, this blue cut has size 3 because it cuts 3 edges, and its smaller side on the right has volume 5. So the sparsity is 3/5. We say that graph G is a phi expander if for all cuts in G, their sparsity is at least phi. Expander have a lot of useful properties. One that be useful for us in this talk is that the diameter of phi expanders is bounded by of logarithm of n divided by phi. Well, unfortunately, not all graphs are good expanders. For example, consider this graph here. This blue cut has only size 1, while both volumes of both of its sides are relatively large. However, each graph can be decomposed into a union of expanders while keeping the number of intercluster edges fairly small. And this is basically the definition of expanded decomposition, and more formally, we call a vertex partition C an expander, an epsilon phi expanded decomposition if each cluster in C is a phi expander, and the number of intercluster edges is at least at most epsilon times the volume of the whole graph. And the expanded decomposition can be seen as a natural clustering of a graph with respect to its expansion or sparsity. How can one construct such an expanded decomposition? Well, the simplest algorithm is as follows. We fix some sparsity phi, and afterwards we find the cut in G with the smallest sparsity. If this sparsity is still bigger than phi, then G is a phi expander, so we can return it as a singular cluster in the expanded decomposition. Otherwise, we recurse on both of the cut sizes and then return the union of the results of the calls. One can see that this results in an expanded decomposition where each cluster is a phi expander by construction, and one can also show that the fraction of the intercluster edges is bounded by O of phi times logarithm of n. This is known to be the best possible trade-off between epsilon and phi. So there is nothing really to be improved here. How can one use an expanded decomposition in other settings? Well, consider the question of constructing a distance oracle. Simplifying a little bit, we say that graph H is a t distance oracle of G if for all pair of vertices in V, the distance between them in G is at least at most the distance between them in H, which is in turn at most t times the distance between them in G. T is called the stretch parameter of the distance oracle. And usually when one constructs a distance oracle, one wants to have as little edges as possible in H while still having a relatively small t. So if one is given an epsilon phi expander decomposition, one can construct the distance oracle with stretch of log n over phi and the number of edges bounded by epsilon times m plus n. The construction is as follows. Recall that expanders have bounded diameter of log n over phi. So we can replace each expander in the expander decomposition with a weighted star, where weight of each edge is equal to this upper bound on the diameter, while keeping all of the intercluster edges. So now we hopefully understand what an expander decomposition is. Now, what is a dynamic stream? This is a fairly simple definition. In a dynamic stream, one is given graph G as a sequence of updates. And each update either adds an HE that wasn't in the graph or deletes an HE that was in the graph. And the goal in dynamic streams is usually to solve some problem using memory sublinear in the number of edges in the graph, because otherwise one can just trivially store the whole graph in the memory and solve the problem after the stream. De facto, a standard approach in this setting is to use linear sketches, and it was first used in this manner by Ann, Guha, and McGregor. And for example, in their other work, they showed that one can construct a cut sparsifier in sublinear in a memory using those linear sketches. Speaking of previous work, there are no trivial results known for constructing expander decomposition in dynamic stream setting. So I will talk about the RAM model a little bit. In the RAM model, one of the earliest works on constructing expander decomposition was by Spielmann and Tank, where they shown that in exponential time, one can achieve the best known trade-off. And their algorithm is a refinement of the algorithm that I mentioned before. For a long, then I will skipping a little bit of the subsequent works. Chernak and Wang shown that in linear time, one can achieve a trade-off between epsilon and phi that is just that is worse than the best possible only by logarithm square of n. And this result was recently improved by Agassi, Dorfman, and Kaplan to have only logarithm of n overhead over the best possible trade-off. In our work, we show that there exists of phi log n phi expander decomposition algorithm in dynamic streams that uses only linear in n over phi squared memory, but uses exponential time. Right? So this has one interesting corollary, that is one can actually construct a best achieve the best possible trade-off between epsilon and phi in a dynamic stream. And another corollary states that now that we have this exponential time expander decomposition construction, we can use it to construct a distance oracle with good parameters in a dynamic stream. We also give a polynomial time algorithm, which has a worse quality trade-off between epsilon and phi, and uses superlinear in n memory, but that still can be made sublinear in m. Okay. For the remainder of my talk, I will talk about the tools that we use to achieve this. First, I will introduce the concept of power cut sparsifier, which proved to be very useful for constructing an expander decomposition. And then I will talk a little bit about the algorithm itself and how it works. Okay, let's start. So to understand why we need a power cut sparsifier, let's try to solve some easier problems first. Let's start with expander testing. So imagine that we are giving G in a dynamic stream, and after we are giving a parameter phi. And our goal is to distinguish if G was a phi expander or had some phi sparse cut in it. This can be done using a delta cut sparsifier. So we could say that G prime is a delta cut sparsifier of G if for all cuts S, their size is approximately the same in G and G prime up to 1 plus minus delta multiplicative factor. As I mentioned before, G prime is computable in nearly linear in n over a delta squared space, in the work by An, Guha, and McGregor. And one can also notice that if G is a phi expander, G prime would be a 1 plus minus delta phi expander, because the sparsity of a cut depends only on the size of the cut, which is plus minus delta preserved in the cut sparsifier, as well as the volumes of the cut sizes, which can be shown are also 1 plus minus delta preserved. So this leads to this simple solution. We just construct a delta cut sparsifier and check if it's a phi expander or not. Okay, let's try to apply the same approach to a different problem, testing if a clustering C is an expander decomposition. And here we are given G in the dynamic stream, then crucially, only after the stream are we giving the partition C and values phi and epsilon. And our goal is to check if phi is an epsilon phi expander decomposition. C is an epsilon phi expander decomposition. So for this problem, if we try to use the regular cut sparsifier, we would run into the following issue, that we would have to check for each subgraph if it is a phi expander or not. And for a subgraph, it is not known if a cut sparsifier preserves the sizes of cuts, right? So we would like to have the following strengthening of a cut sparsifier, and that is a graph G prime, such that for every possible cluster C in V, G prime restricted to this cluster C would be a cut sparsifier of G restricted to this cluster C. However, such a sparsifier G prime would have to have almost the same number of edges as the original graph, which would render it basically useless. And the reason is pretty simple. So consider any two vertices U and V in the graph. Right? If you now restrict our G prime to those two vertices, then by checking the only non-trivial cut that separates U and V in the subgraph, we could determine if the original graph G had an edge E or not, right? So that would imply that G prime would have to have at least this approximately the same number of edges as G, which implies that it would have to have a lot of edges. That's bad for our purposes. However, we don't exactly need a guarantee, a purely multiplicative guarantee for the cut size preservation to check the sparsity. We can relax it to have a additive error also in the volume of a cut. So for example, we say that G prime is a delta epsilon cut sparsifier if it has 1 plus minus delta multiplicative error in the size of a cut itself, as well as additive error in between 1 plus minus epsilon times the volume of a cut S. And it's pretty easy to see that if G is a phi expander, then G prime would be an 1 plus minus delta times phi plus minus epsilon expander itself. That would allow us to check that G is a phi expander if, well, epsilon was relatively small compared to phi in this construction. And similarly to the strengthening that I proposed earlier, we can strengthen this concept to the concept of delta epsilon power cut sparsifier, where for each partition C, you would want with high probability that for all clusters in this partition, G prime reduced to each cluster would be an delta epsilon cut sparsifier of G restricted to this cluster. Okay, and if we had such a power cut sparsifier, then the solution to our expander decomposition testing would be pretty simple. You would just construct G prime, then you would check the sparsity of all of the cuts in each cluster, and then we would make our decision. However, there's one problem. How to construct such a cut sparsifier? Well, let's take a step back and look at how sparsifiers are constructed in general. First, people define some kind of edge importance for each edge, depending on the kind of property that they want to preserve in a sparsifier. For example, we can take just reverse edge connectivity, right? Then this importance is multiplied by some factors to get sampling probability PE for each edge E. Then each edge is sampled with its probability and assigned weight equal to 1 over P if it survives the sampling. In our case, we say the sampling probability to be proportional to the sum of inverse degree of the edge endpoints. And this is good for two reasons. First, this is a very simple importance measure to compute, even in a dynamic stream. And second, this sampling probability was considered earlier by Spielman and Tank, and they shown that sampling with this probability would produce a cut sparsifier if we were to apply this procedure to an expander. So bottom line is that power cut sparsifier, while being a new object, is not exactly a new object by itself, but just a more finely grade analyzed previously existing object. Okay, so now let's take a look at how our algorithm actually works a little bit closer. So if one were to think about how to construct an expander decomposition in dynamic streams now, one could try the following approach. Just compute the power cut sparsifier G prime and construct an expander decomposition with hoping that because with high probability this expander decomposition can be verified as a power cut sparsifier, then it would be an expander decomposition of the original graph. However, there is one problem, and that is the high probability property of the power cut sparsifier only holds if the partition was chosen independently of the power cut sparsifier. And this is not the case here, because the partition is very much depends on the power cut sparsifier itself. So we cannot use this approach. So we can try something else. Okay, recall the recursive approach that I mentioned in the beginning of the talk. We take our graph, we find the graph with the smallest sparsity, we make this cut, we recurse on the subgraphs, and so on. So what we can do is that we can take graph sparsifier G prime 1, use it to find the sparsest cut in it, then recurse on the subgraphs, but for the subgraphs use a different cut sparsifier G prime 2, and so on until if we can verify that the graph is a expander itself. This works, but this has one problem, and that is the total memory used would be the number, the depth of this procedure times the memory needed to store one cut sparsifier. So to achieve near, almost linear memory in N, the depth must be polylogarithmic in N. And the simple algorithm that I mentioned earlier doesn't have this guarantee, so we need to improve the algorithm a little bit. So we use something called a cut matching lemma, and this lemma is a member of a family of lemmas with similar guarantees. The guarantees looks like this. So there exists an algorithm which takes as an input a graph G and sparsify and returns one of the following. It can declare that G is an O-phi expander, or it can return a graph with sparsity less than phi, but that is a fairly balanced one. In terms of the volume, that is the volume of the both sides is approximately the same. Or it can return a graph, a cut S that has a sparsity less than phi, and that doesn't exactly has that doesn't necessarily has the guarantee that it's balanced in the volume, but it can give us some property on the bigger side of the cut. And this property can be a lot of different things. Well, the strongest one that is that people can get if they apply this cut matching lemma approach to a graph in a classical model is that the bigger size of a cut is the O-phi expander. This was shown by Spielmann and Tank. And in this case, we can just stop our recursive algorithm at this point. And yes, this would bound the total depth by O log n. If we don't want to pay exponential time, as is the case with the first type of guarantee, the guarantee that we can get is O phi expand is that the bigger side of a cut is nearly O phi expander. And there we can there's also a possibility to get a weaker guarantee that just that the bigger side of a cut doesn't have a cut that is comparable in that is bigger in volume than our cut and has sparsity at most phi. And as it turns out, in our setting, because we use cut sparsifiers to find the cuts, we cannot really make you get a cut matching lemma that gets us a strong guarantee like the first one, but we can only get something similar to the first guarantee. And that's basically all I wanted to say about our algorithm. Now let me talk about some open problems. The first open problem is to try to remove dependence on parameter phi, and we are working on it right now, so stay tuned. The second open problem is try to improve the quality trade-off for the polynomial time algorithm, preferably to match the ones that we get in a classical setting. And finally, it would be very interesting to construct an algorithm that would allow the stream to be adaptive. That is a setting where we are required to output our expander decomposition at some point in the stream and then continue to receive the updates. And that's all I wanted to talk about. Thank you for your attention.